Now we're going to learn our last, but maybe best. I don't know, if you had to rank them, it's tough to say. I mean, I guess the power rule is pretty crucial, so maybe that's number one. But chain rule, this is definitely up there. It's definitely in the top 3 out of derivative rules. So there's that. So we need to learn what the chain rule is, how to use it, when to use it, and really actually just understand that we've kind of been using it already. It's the derivative of the composition of functions. So let's look at that. So first I want you to go ahead and find the derivative of this function. You should be able to do this. Pause the video, unpause when you're ready to check. Alright, so you should have done this by, I can multiply this out. So f of x is actually 25x to the 4th minus 30x squared plus 9. So then derivative, I can do a simple power rule. Bring it on the 4, subtract 1, 100x cubed minus 60x. So that's my derivative. Pretty straightforward. I don't need anything else that I don't already know how to do in order to find this derivative. But what if instead of 2, this was 20, right? I do not want to multiply that out. So there's got to be a better way. Yes, there is. Look at that. Set myself up. It was nice. So that's where the chain rule comes in. It deals with the composition of functions. So this is one thing where this notation is going to look confusing. Don't let it confuse you. Remember? Don't be confused, and then you won't be. It's pretty simple. So if I have some function f of u, so that means I have a function with respect to some variable u, it's differentiable with respect to u, but u is some function g of x, which is differentiable with respect to x. So then I can say that I have some y equals f of g of x, which is then also differentiable with respect to x. So the derivative of y, or dy dx, the derivative of y with respect to x, is going to be dy du times du dx. Another way to write that, so if I just write it this way, what's the derivative of f of g of x? It's the derivative of f of g of x times the derivative of g of x. So how does this work? Well, again, similar to the quotient rule. Whenever I'm doing the chain rule, there's something I'm always saying to myself. And the way that I talk to myself while I'm doing the chain rule is I always say the derivative of the outside times the derivative of the inside. Because that's what we're doing. That's what this notation and this notation is telling us. So if we take the same function that we just took the derivative of, but now we do the derivative with the chain rule, it's going to look like this. So I can go right to my derivative. So the outside function would be the function x squared, because I can think of this whole thing as something squared. So I'm just going to do the power rule. So I'm going to do 2 times the inside stays the same, 5x squared minus 3, and then I would subtract 1, so this would be to the first, and then times the derivative of the inside, so that would be 10x. So this would be my derivative. Now again, we could multiply this out, and if I multiply this out correctly, then I'm going to get, okay, 10 times 5 is 50, 50 times 2 is 100, x times x squared is going to give me x cubed, so I get my 100 x cubed, 10 times 3 is 30, 30 times 2 is 60, so I get minus 60x. So I get the same derivative. So to try to emphasize the composition of functions point, I would think of this, I would say, okay, f of x is some function h of g of x, where h of x is x squared, and g of x is 5x squared minus 3. So then when I do h of g of x, I take the g of x function and I substitute it in here to get f of x. But as I was saying, when I'm talking about doing the derivative of the outside part is the h of x function. So the derivative of that was just a simple power rule. Brought the 2 down, subtract 1, and then the derivative of the inside is the derivative of the g of x function. Okay, this leads to what we call our extended power rule. Again, this is really just a formality. we're already doing this. So I'm showing you this hopefully to not confuse you, but because it's something that's in the book, it is a notation thing. But again, we're already doing this. So all this says is we have our power rule that we've already been doing. This is our power rule. This is another example of our power rule, where we bring the exponent down and subtract 1. Here it's in terms of u, but it's the same thing. Bring the exponent down and subtract 1. But what if I want to take the derivative with respect to x of some function u? Then this is saying bring the exponent down, subtract 1, and then do the derivative of u with respect to x. So again, that's exactly what we did in that first practice problem. But as I was saying, we've already been doing this, and if we think about like y equals x squared, well, if I want to find the derivative of that, y prime equals 2x to the first, and then the chain rule is telling me that I'm actually going to do times dx dx, or times the derivative of the inside, but the inside is x. So what is dx dx? Well, that's 1. So I actually get y prime equals 2x times 1. But we don't write that, so that's why in general we just say that y prime equals 2x. So this is just extra work that we don't have to do because we know that dx dx is 1, or the derivative of the inside here, which is x, is 1. Because we learned that the very first day that we learned our rules, our shortcut rules. So again, this is just demonstrating we've actually been doing the chain rule. We just didn't think about it that way because the derivative of the inside so far has always been 1. Alright, I want you to try this. Pause the video, unpause when you're ready to check. Alright, so hopefully you got y prime is 280 times the quantity 3x squared plus 4x minus 5 to the 279th, and then times 6x plus 4. Don't simplify this at all, just leave it. Alright, how do we get that? So again, just trying to show you this composition of functions idea. Hopefully you got that, but if you're still confused about this, I can say, okay, well, I see that I have some quantity raised to the 280th, so I'm going to do a substitution. So I'm going to say u equals 3x squared plus 4x minus 5, so then y is actually just u to the 280th. So what's the derivative of y with respect to x, though? And again, that's why it's really important to understand this. When we say derivative, what are we taking the derivative with respect to? Because this can change. I can do the derivative with respect to y, I can do the derivative with respect to u, I can do it with respect to whatever variable I want, but I need to denote that or talk about that or say that. So in this case, the derivative of y with respect to x is 280u to the 279th times du dx, or the derivative of u with respect to x. So, but what was u? U was 3x squared plus 4x minus 5, and what's du dx? That's 6x plus 4. Okay, so it's really important that we understand the chain rule. It's a crucially helpful rule for derivatives, and it's going to come up a lot. So it's very important that we understand it, how it works, why it works, and all of the above. Really, it's just the composition, the derivative of the composition of functions, though. So the way I like to think about it, derivative of the outside times the derivative of the inside. If you have multiple functions, you just keep working in. So the derivative of the outside times the derivative of the inside times the derivative of the next inside times the derivative of the next inside, and so on.